So the screen is still visible, I guess.
Yes, sir. Visible,
Okay,
sir.
fine. So I'll just start.
Okay, sir.
So today's idea is to factorize polynomial over finite field. So let me start with that. So as it is the, I mean, as I said several times, that you can just interrupt me anytime if you have a question. I mean, you don't have to wait for the end of the lecture to end, so you can simply ask.
Okay, sir.
Yeah. So, mm, so what we want to do is to factorize polynomials. So factorization. So factorization in FQX. So Q is a power of a prime. When we work out examples tomorrow in the tutorial, we would use just prime because power of prime would make things more complicated. And the algorithm we are going to discuss is if uh, so what to say, it's the mother of all known algorithm for character this factorization of polynomials over finite field, but uh, it's inefficient in some ways. There were some things in the algorithm which are not very efficient. So calculating for large prime and prime power would be a bit difficult if we exactly follow the algorithm. So the best possible algorithm available are modified version of this. So anyway, let's start with the thing. So our final aim is to write down an algorithm which will factor polynomials in FQX. So what we want to do is the following. So let fx be a monic polynomial. So it's enough to consider monic polynomial. Be a monic polynomial of degree n. So degree greater than equal to 1. We are not looking at constants, of course. So we want to write so we want to factorize fx as, or we just write f. So f is as f1 power e1 to fk power ek for some k. For some k greater than equal to 1, and where all these factors are irreducible polynomials, where f1 through fk are all elements of the same ring, same polynomial ring, but they are all irreducible. So they are all irreducible, and we started with a monic polynomial f, so all these are also going to be monic. Are irreducible. So all of them are irreducible. So that is what we want to do. And the C1s are all greater than equal to. So EI is greater than equal to 1 for all I. So this is what we want to do. So if f itself is irreducible, then k is going to be 1 and so k is going to be 1 and e1 is also 1. So we note that it's enough to know how to factorize a polynomial where these factors do not repeat. The irreducible factors do not repeat. namely E1 through EK, all of them are 1. It's enough to know that. So we note that it is enough to factorize f where E1. Okay, so enough to factorize, I would just write square free f. Enough to factorize square free polynomials. So that square of no polynomial divides it. So square free, factorize square free f, square free polynomials. So square free polynomial corresponds to these exponents being all equal to 1. So if we know how to factorize this, we can factorize polynomials which are not square free as well. The most important idea is in the following theorem. So let me write it down. So let fx let's write so fx and hx in fq x, the polynomial ring, b, so both are monic non-constant polynomials. So write it monic non-constant. So they are at least of degree 1, not degree 0. So monic non-constant polynomials. So both are monic non-constant such that hx power q is hx modulo fx. So this says that if we raise hx to power q, q is the same q as the q of the finite field, so number of elements there. So hx power q should be hx modulo fx. So that's the condition, such that this is true. Then fx is equal to a product. So this is GCD of fx. So GCD of two polynomials hx minus c, where c is an element in the finite field, and then we take product over all elements of the finite field fq. So what we are saying that fx and gx are monic non-constant polynomials, satisfying this condition that hx power q. So if you just raise the polynomial to the qth power, then it's going to be hx modulo fx and reduce modulo f. So then this is true. If this holds, then fx is equal to product of these polynomials. So this factors here are GCDs of fx and hx minus c. So we subtract c from there, and c is an element of the finite field, and the product runs over this. So this looks like a factorization, but it might be trivial in certain cases. So we would discuss that. Let's prove this first. Proof is easy. So just note that each of these GCD of course divides fx, because this is GCD of fx with some other polynomial, so that is definitely dividing fx. So uh, each GCD on RHS, so on the right hand side, divides fx. So each one divides fx. Each one divides fx. For, of course, that does not mean that the product also divides. So that's what we have to show. So if we show that this, all these GCDs uh, are distinct, then then they all must divide fx simultaneously. The product has to divide fx. So that's what we want to show, that for C1 and C2. So if I take two elements in FQ such that C1 and C2 are not equal, then the GCD of Hx minus C1, sorry, Hx minus C1. So we're looking at the GCD of these two polynomial, Hx minus C1 and Hx minus C2. This GCD is 1. This GCD is 1. So that is easy to see, and of course the monicness of H is of use here. So if so the GCD of these two divides both of them, so it divides the difference, and the difference is C1 minus C2, which is an element of the field, and so that's an element of the field. Now these polynomials are monic polynomials of so that's an element of the field. So GCD can at most be an element of the field. It's not a polynomial. It has to be an element of the field because it divides the difference. So it has to be an element of the field. And since these Hx is a monic polynomial, so that element has to be 1. So GCD is 1. Now each of these factors, so when I if these GCDs are if this GCD is 1, then there is nothing common between two such factors. So GCD of fx hx minus c1 and GCD of fx hx minus c2 doesn't have anything in common, and both of them individually divides fx, so their product has to divide. So therefore RHS divides fx, because each one divides and there is nothing common between them, so their product also has to divide. So RHS divides fx. Now if we can show that the fx also divides the product, this RHS, the right hand side, the product on the right, then we are done. So how do we show that? And for that we require this condition, that condition we assumed. So next, what we look at is this condition. Okay, so now So what we have is hxq is hx mod fx. So I just go to the next page. Mm. So this is the condition we have, just to recall this. So that's the assumed condition on hx. And observe that hxq minus hx is going to be a product hx minus c. In fact, this is at the heart of the proof. So, and this simply follows from what we already know. So we have shown that if you take an indeterminate, then over this finite field uh, if q, then what we have is y minus c in fq. So this is an equality which we have proved last time. So here simply the indeterminate is replaced by the polynomial. So that is obviously true in this case. So, okay, let me just write it legibly. So this is sorry, this is product over hx minus c in fq. Yeah. Uh, so let's look at this condition. So so with this condition, the assumed condition, let's call it star. So now this star implies that fx divides this difference. So fx divides this left hand side. So fx divides the right hand side. So fx divides the right hand side. And that's it. So because if it divides this product, then of course it is going to divide uh, if we replace all the factors by GCD of this thing with fx. So this is a direct consequence of this. So so what we have shown is that the product on the, yeah, this is our theorem. So let me give the name to this equation. So in equation 1, the right hand side, so we first show that the right hand side divides fx, and then we showed that fx divides the right hand side, the product on the right hand side. So both sides are equal. So right hand side divides left hand side divides right hand side, so they are equal. So that completes the proof of this theorem. And now so this completes the proof. Now let's think about this. So just let me change the color. So remark. So what we have now is is what looks like a factorization. It is a factorization, but the problem is it might become trivial. It might simply give you fx equal to fx into 1. It might simply give you this kind of factorization that all so one factor is fx and all others are 1. All other GCDs are 1 and only one GCD is exactly fx. That's possible. So if fx divides, if in particular if fx divides one of this, so suppose it divides uh, divides one of these factors, so fx hx minus c for some c, some c in the finite field, then the GCD, that GCD is just 1 and all other GCDs, because all of them are relatively co-prime to this one, all the others are relatively co-prime to this, what we would get is just a trivial factorization, fx equal to fx into 1. So then the GCD of fx hx minus c is just fx because it divides, fx, and for everything else, or maybe we just put a c1 here so that we can write it, and all other GCDs are going to be 1, simply because they are relatively co-prime to this one. So C is 1 for all C not equal to C1. So therefore we get a trivial factorization. So we get a trivial factorization, which we want to avoid. Trivial factorization. Now, if this method gives a non-trivial factorization, then the polynomial hx is called f-reducing polynomial. So we just write it like a definition. So if hx gives a non-trivial factorization, so by non-trivial factorization, I mean that it's not of that type. So we are actually factorizing into polynomials of into non-constant polynomials. So they would all be of degree less than the degree of fx. So if we get a non-trivial factorization, so non-trivial factorization may not be factorization into irreducible. That is another issue. So we have to do that, but at least some factorization. So if hx gives non-trivial factorization, first of all, we want to factorize in a non-trivial way. Then only we can look for irreducible factors. So gives a non-trivial factorization, then hx factorization of fx. I wanted to write of fx. Then we call hx an f-reducing polynomial. So an f-reducing so an f-reducing polynomial. That's just going to be our name. And so now we want to know that how do we find a f-reducing polynomial? So we want to find an hx such that it gives a non-trivial factorization. So the following conditions would be enough. So that is, let me write that. So we know that I would explain. Any hx satisfying hx in in the polynomial ring satisfying these two conditions. So first condition is what we started with, that the qth power is equal to hx modulo fx, and second one is it is a non-trivial uh, sorry hx, so degree of hx is strictly less than, so it is a non-trivial polynomial, meaning it is at least of degree 1, it's non-constant, it's a non-constant polynomial at least degree 1, and its degree is strictly degree is strictly less than fx, degree of fx, so that we don't end up getting this kind of problem, so that fx does not divide this thing. So if fx divides, then it has to have degree at least f, at least equal to the degree of f. So that does not happen. So if we have such an f, so if we have an f like this, whose degree is, which satisfies the condition we want, that is, this is the condition in the theorem, and also the degree is strictly less than the degree of fx, then it is an f reducing polynomial. So satisfying this is f reducing. So this kind of polynomial will do the job. So that is all right. But now what we want to find. Any question up to this? So if you have any question.
How to find f of x?
Sorry.
How to find h of x? So once you know the h of x, we can factorize, right?
Yeah. So that exactly. So that's the next point. I mean, that's the most important point. That how do we find h of x? I mean, we know all these. So given a polynomial, how do we find it? Yes. So that's what So essentially, the rest of the discussion is addressing that question. That how do we find such fx? Is such a hx? Yes. So once we have, we can factorize. Yes. So that's the most important question, in fact. So construction. So I would just write a title like construction of f reducing polynomial. And our initial assumption, whatever we started with, remains. So namely, f is a square free polynomial. So when we factorize, it will factorize into distinct irreducible polynomials, and it is monic. So these two assumptions are with us. So f is, so suppose f is now f1, f2, fk, product of distinct irreducible polynomial. So if f is equal to this product of k distinct k distinct irreducible polynomials. Now let's look at a k tuple C1, C2, Ck. So this is a k tuple in FQK. So this all these coordinates are elements of FQ. So just if so just a k tuple. Now what we want to use, we want to use Chinese remainder theorem for polynomials. So by CRT, Chinese remainder theorem with all these polynomials. So f1 to fk. So they are all distinct irreducible polynomial. So they are co-prime. So we can use them. So by CRT, so Chinese remainder theorem for polynomials. Uh, Polynomials in FQ. It is just exactly the, if you have seen it, it's fine. Otherwise also it is just it is exactly the same as the Chinese remainder theorem for integers. Just the same. So by CRT, there exists a polynomial hx in FQ x satisfying satisfying all these congruences. So congruence is hx is congruent to ci mod fi x. So these polynomials. So we are using these irreducible polynomials. This happens for 1 to k. So all of them. So that's the system of equations, system of congruences we are using, and hx is a solution and which exists by CRT. And it's a solution modulo fx, so its degree is less than the degree of fx, and the degree of hx is less than degree of fx. So that's directly from CRT. So now let's look at this hx and raise it to the power q. So if we raise it to the power q, then this is, so we are working modulo fi. Then this is ci power q modulo fix. And this is going to be exactly equal to ci, because the ci is an element of the finite field fq. So qth power equals the element. This is exactly equality, in fact. And then ci, and then this is hx modulo fix. So this happens for all. So 1 less than equal to I less than equal to k. So for all fi's, and all of them are distinct irreducible polynomials. So if each one divides this difference, then the product divides, because they are distinct irreducible polynomials. So they do not have common factors. So if each of them divides, then of course the product divides. So if 1 to if k, the product divides hx q minus hx. So individual, just let me write it. Or I just put the f1 of x to, so product of this fk of x, so this product of this k polynomials that divides hx cube minus hx, and this is fx. So this is the fx we started with. Fx is this, so fx is f1 f2 fk. So that's precisely fx. So so hx cube minus hx, sorry, I can just write that this is congruent to hxq is congruent to hx modulo fx. So this is what we get, and this is what we wanted. And also by CRT we have this degree condition. So so this fx is a perfect solution for our f reducing polynomial. So therefore, so let me write that say 2 and 3. So by 2 and 3, hx is f reducing polynomial. So it is, this polynomial is going to give a factorization. It need not be factorization into irreducible, but it is going to give us some factorization. Is f reducing polynomial. So it is indeed an f reducing polynomial, but we are still in theory. So we don't know how to find it. We just figured out that we can use CRT to construct, but we haven't constructed. So that is the next thing. So we want to actually construct. So we want to, because the idea is to write an algorithm. We want to use a computer program to actually give us the factorization. So let's analyze how we got the solution. So and how to go about it. So what we have done, we have used CRT to this effect, that we looked for solutions of of this system of congruence equations, that hx is congruent to ci modulo fi. So this is the system of congruence equation, and we looked at the solution, and that what.
So the factorization is unique up to order. Suppose we have the HF is not unit, right?
Yeah, no.
So maybe
is not
we
unique.
get.
Yeah, in fact, I mean, at this stage, the factorization is just a non-trivial factorization. So, I mean, unless we really factor it completely into irreducible, we do not have any uniqueness.
Now, suppose we have a H1, H2.
Yeah.
So for H1 we have a factorization. For H2 we have a factorization.
Yes.
These two factorizations are.
Could be different because if they may not be
Okay, this is irreducible.
Yes, exactly. So they may not be irreducible. So different kinds of reducible factorizations.
Okay.
And just for example, just the integers also can be factored like that. So and 12 is 2 into 6 and 3 into 4. So that's the kind of thing will happen.
So can we see the number of base we can write above excessive factors?
Yeah. So I'm just going. Yeah, exactly. So you are actually going ahead of the thing. So yeah, that's very nice. So that is what we are trying to do it. So how do we actually pinpoint such a? How do we construct? And yeah, let me say that. So it's precisely the answer to this. So let's start by this. So. Let me write it in this way so that we've so so first step is a bit it's not clear why we are doing it, but once we just go to the second step, it will be clear why we are doing it. So let x to the iq. So I'm looking at, okay, let me write it for 1 less than no, in fact 0 less than equal to I less than equal to n minus 1. So just recall that the degree of fx is n. So from from 0 to n minus 1, we look at x to the iq. So if q is 5 and this degree is say 3, then we are looking at x to the 0, x to the 5 and x to the 10. And then reduce it modulo fx. So reduce it modulo fx. So we write that. So that will be, so if we reduce it modulo fx, that will be a polynomial of degree at most n minus 1, because f is of degree n. So I'm writing that polynomial as these coefficients. So I just write out the polynomial ij. So I'm trying to index it by this I also, just keeping track of that index, x to the j, and j should be from 0 to n minus 1, because the degree can be at most n minus 1 modulo fx. So that is always true with some coefficients. So all these coefficients, so bij's, are coming from fq. So they are just finite field elements. Bij. Yeah. Now suppose fx is a0 plus a1 of x plus a n minus 1 x to the n minus 1. So so this is also a polynomial. So so suppose hx looks like this. So a polynomial of degree at most n minus 1. So these coefficients can be 0. 0 is allowed. So the degree is at most n minus 1, not necessarily equal to n minus 1, at most n minus 1. So this is the f reducing polynomial we want to. Hx is our f reducing polynomial. So we want to see how to do it. So since we want this hx to satisfy this condition that qth power is congruent to this condition 3 and this equation 3, we want h to satisfy this. So we would raise it to the power q. So now we have written out the coefficients. So this is going to be a0 plus a1 x to the q plus a2 x to the 2q. It's a square, so x a square, a2 x a square, so that would be x to the 2q, and then a n minus 1 x to the q minus q into n minus 1. Yeah. So coefficients, of course, do not change because q is this is the order of the finite field. So if we raise any element to the order of the field, it remains the same. So the coefficients just do not change. And now we know how to, we have already written out these powers. So this is the reason we wrote out these powers, only these powers, this x to the multiples of q. So powers of x which are multiples of q. So that is the reason we wrote out this. And now we are ready to write this polynomial modulo fx. So let me try that. So a0 is so I is 0. So I is 0 for a0. So this is b of 0 0 plus b0 1x plus b0 to x square plus b0 n minus 1 x to the n minus 1. Let me write out a few so that a1 b so just indexing is the second the first one, yes. So b10 plus b11x plus b12x square b1 n minus 1 x to the n minus 1, and so on and so forth till we reach a n minus 1. So that is n minus 1 0 plus b of n minus 1 1 x and ends with n minus 1 x to the n minus 1. And what we, so this is what we wrote. So this is modulo fx. So we simply raised, so consider this to be hx. So just write out it in terms of this coefficients, a naught to a n minus 1. And we raised it to the power q. And since we have already written these powers x to the multiples of q, so powers are all multiples of q, modulo fx. So we can use that to write hx power q modulo fx. So it is going to be this. It's going to be this. And what we want, so this is what we want. So if hx to the q is h of x, this is what we want, that hx to the q is modulo fx, it is h of x. So we want this. So the right hand side, so this whole thing should reduce to h of x. H of x is, so h of x is a naught plus a1 of x plus a2 of x square up to a n minus 1 x to the n minus 1. So what we have now, let me just write it, what we want. So this implies, so obviously you must have guessed by now that we are going to use matrices and write these coefficients as vectors. So let's use that notation now. So that is simply going to imply that a n minus 1, if you write out the coefficients as a vector with entries in FQ, then this multiplied with this matrix B, I would just write what the matrix is. You want this to be A1, you want this to be AN minus 1. So this is what we want. So this equation is this equality would be true if this happens. In fact, this is actually an equality in this case, because hx, the degree of hx is going to be less than no, what I'm saying is wrong. No, it's not. So it's a modulo relation. So what we are looking for is this. So if we can, so now we are down to this linear system of linear equations. So we want to solve them. And okay, let me write this B first. So where B is this matrix. So B is let me write that. So B 0 0 of, so the, so I think it is b1 0 bn minus 1 0. Yeah, let me check with this. So if I'm writing this coefficients as a row vector, so a naught is getting multiplied with this, so this should be my first first column. So that should be my first column. So in fact we can just write out like this. So this should be my first column, second column, and like that. So that's the case. So then on this side it is b1 sorry 0 1 0 1 b0 2 and so on, b0 n minus 1 b1 1 b1 2 b1 n minus 1 and so on and so forth, the last entry being n minus 1 bn minus 1. So what we now have to do to find an f reducing polynomial is to solve this system of linear equations. And what is this system? So this system is simply I can just take the identity matrix, subtract it to b, then this a this vector is an element of the null space. So this b minus I is 0. So we are simply looking at null space of this matrix. So that is what we have. And now so let's go back to the beginning of this construction. So what we have seen here, the initial discussion. So if f factorizes into k factors, if f factorizes into k factors, k irreducible, distinct irreducible factors, then for every k tuple over fq, we have a polynomial. So given any k tuple, we could construct one. So our system should be having q to the k solutions, right? So because for every given any k tuple, we can construct. So we use CRT to construct this hx which satisfies this, and that in turn satisfies the condition we want. We get an f reducing polynomial. So we should be having q to the k solutions of this system that we develop. So this has q to the k solutions. So we have q to the k solutions of this. And k is the number of this. So that would simply mean, because these solutions belong to the null space, so that would simply mean that the dimension of the null space is k. So therefore, the dimension of null space, let's write null space of b minus I is k. So the dimension of the null space is k. In fact, once we construct this matrix and find the dimension of the null space, we know how many irreducible factors f should have. So that's a very interesting information. That just comes from the dimension of the null space. So now these are things which we can do. So that's most important. So that is dimension of the null space, and that's also going to be equal to so which is equal to the number of distinct irreducible polynomials, equal to the number of distinct uh, irreducible factors of fx. So there is one more thing to notice, which is here. Yeah. So one second. Yeah. So it's here. So this is an important thing to notice from this. So what we have written here is x to the iq, where I is from 0 to n minus 1. So it includes 0. So let me just change color. So x to the 0, which is just 1, and that is written out as b00 plus b01x plus etc. plus b0 n minus 1 x to the n minus 1. That's just from our notation. So that simply means that this vector, so that would imply, okay, it's really towards the end. Maybe I just write it later. So this is too close to the edge. So let me write it again. So just note that. Let me just put a star or something on this. So we know that from this this star, so x to the 0 is written in this way, that b00 plus b01. I hope I'm not making a mistake again. So this is yeah. So 0 is, so this is 0, and the second one is running index. So just don't want to make a mistake on the index. So this is b00, b01, b02 x square, and to b0 n minus 1 x to the n minus 1. So x to the 0 is just 1. So therefore, this vector b00, b01, b0 n minus 1 is simply 1, 0, 0, and all zeros. So that's the vector. So n minus 1 0 and the 1 in the beginning. So so one of these sorry, this is what I have written later. So and that's the first row. So first row is 1 0 0 0 0. So all zeros. So first element is 1 and everything else is 0. So let me just add a page after this. So we know what the first element is. Sorry, first row is first row of B, and that shows that 1 0 0 0 is always a solution. So so therefore so I'm just continuing with that. So okay, let me just, so that this is the reason, and then we observe that. So that is that leads to the observation that 1 0 0 0, this vector is always a solution. So this is a solution. This is a solution. This is a solution to this equation. I think we have equation number up to 3, so that should be 4. This should be 4. So is a solution of 4. And what we now do is the following. So we noted that the dimension of the null space, because we have q to the k solution, so the dimension of the null space of b minus I is k, and one of the vector is this. So we have k minus 1 other vectors so we have a basis. So there exist polynomials h2 of x, h3 of x to hk minus 1 of x, sorry, hk of x, k of x, all of degree degree n minus, degree at most n minus 1, at most. So all of them degree at most n minus 1. So these polynomials corresponding to the basis vectors of the null space of B minus B minus I other than this 1 0 0, this other than 1 0 0 0. So we are interested in the other ones because the first one, this 1 0 0 0, this one gives rise to the polynomial 1. So h1, the first polynomial what we get is just 1. So that doesn't help us. So even though it satisfies everything, it doesn't help us. It's not a f-reducing polynomial. So with this, let us see how the algorithm will try. So how we actually do this whole process. So given a polynomial, how do we start? So I have actually written out all the entire algorithm. Let me just go over it slowly. And yeah, so please stop me whenever. So whatever question you want to ask. And this algorithm is due to Barleykamp. So Barleykamp so this okay, let me explain the algorithm, then I would discuss for some slight inefficiencies in this algorithm and where does the inefficiency come from. The algorithm starts with a monic polynomial of degree n. So we are given a monic polynomial of degree n over fp. So I'm just, because the worked out examples that we are going to do tomorrow would also be on fp. P is a prime, because as I said in the beginning that if as you take even bigger p, so this will actually efficiently work for small p. For large p or powers, it's going to be complicated. In fact, the software I'm using, this Sage Math, I do not know about other software. At least in this software, the way this uh, polynomial, the way this finite fields of uh, higher degree. So if p to the n. So if you want to consider a finite field with p to the n elements, where p is a prime, n is a positive integer, then that is constructed via the quotient of the polynomial ring. And so the representatives of that field looks like, so they look like polynomials. So if you want to consider a polynomial ring on that, so that will look like polynomial in two variables. So I don't know how to handle them in Pro. So that can be quite clumsy. So we would simply stick to prime fields. So we stick to fields whose order are prime and small prime. In fact, p is a small prime. So anyway, let me just explain how it works. So as such, the algorithm would work for any q. So p replaced by any q. Q is p to the n. So it will work for any finite field, but this is the case we would actually be doing. So fx is a monic polynomial of degree n. The first step is to reduce these powers x to the iq. Sorry, this is not q. That's a mistake. This is not q. This is p. So I just did what I just said. So this is p. This is p. It is p. I was, so we were using q in the theorem because in the theoretical work, because it is it's fine for this. So any algorithm will work whatever you take. So reduce x to the ip. So these are powers like, so you are looking at, in fact the first one is just 1, so there is nothing to do. Then you look at x to the p, x to the 2p, x to the 3p, and so on. Of course, depending on what the degree of f is. And finally, what you are looking at is p into n minus 1. So if the degree of f is 5, then this is up to 4n. So you look at them, look at these powers and reduce them modulo fx. So polynomial congruence. Just first step is just simply polynomial congruence and note down these coefficients. So these coefficients are required for the next step. So next step is to form the matrix. So we form this matrix. I wrote it here. So if Bn is this matrix, so we write down this coefficient matrix. And the first thing is to find the rank of this. So it's not actually necessary. Just looking at the null space will do, but you can as well do this. So just find the rank of this so that we know how many irreducible factors f has. So that's very interesting. So suppose R is the rank, and then write k as n minus r. So k is, so just remember that what we did in the theory, that k is the number of irreducible factors. So that is what we were having. So that's the step of the algorithm. So that is this step of the algorithm. So if k is 1, that is the null space is of dimension n minus 1. So if k is 1, sorry, null space is of dimension 1 and rank is n minus 1. So if that happens, then fx itself is irreducible and we stop. So we will just terminate the process. If k is greater than equal to 2, we go to the next step. And what is the next step? So we look for a basis of the null space. So we look for a basis of the null space. So we have these vectors. So the dimension is dimension is k. Dimension of the null space is k, and because this k is n minus r is the rank, so that's the dimension of the null space. So dimension of the null space is k, so we have this basis. So we construct a basis. So C1 to Ck, and as we noted earlier that the first vector is just 1 followed by n minus 1 zeros. For each of these, we construct polynomials. So we have this k basis element, we construct polynomials. So how do we construct polynomials? So we look at just these vectors and so we look at these vectors. So Cj bar, so this vector which I have written out as Clj. So this is like so how does it look? So C0j to C1j Cn minus 1j. So that's the kind of vector we wrote out. And so once we have this, we construct polynomial. So these are going to be the coefficients of the polynomial. So x to the 0 has the first coefficient, so that's the constant term. Then this is the coefficient of x square, up to coefficient of n minus x to the n minus 1. Many of the coefficients can be 0. Like for example, for the first one, all of them are 0 except for the first term, which is 1. So whatever they are, so just construct them. Now pass to the next step. So what we have is just forget about the first polynomial because the each one I didn't even write here. So if you write it out, it would have just it's a constant polynomial 1, so that is of no use. So we would have k minus 1 polynomials which we can use. So k minus 1 non-trivial polynomials, non-constant polynomials. So now take the first one. And so this H2 exists because k is greater than equal to 2. So at least you have one more polynomial. So it is at least up to 2. So you have H2. So take the first polynomial and calculate the GCD. Calculate the GCD of fx and H2 of C. Calculate all the and then multiply all of them, and we know that this is equal to that's what we proved. So whatever polynomial we take, this is going to happen. That we have seen. So that was our starting idea. So we write this factorization. So if this factorizes f completely, meaning if we get k factors, so there is an interesting thing. So if we get k factors out of this working, then we can stop because they have to be irreducible. It has k factors, k irreducible factors, and if we write it as k factors, then they have to be all irreducible. So they are all distinct. That we have seen that they are all distinct. So if we have all these k factors, then we stop. So if not, then we take the next polynomial H3. So we take the next polynomial and calculate and do the same process, actually do the same process with whichever so whatever non-trivial factor we get in step 4. So suppose we get a factor which is gx, so we then consider the GCD. So So that's what I'm saying, that otherwise calculate GCD of gx and h3 of x, the next one in the line, minus c for all of this, and then write, so for all non-trivial factors of hx found so far, and just continue with this. And this procedure is going to terminate. This is going to terminate. Uh, yeah. So of course the last statement requires a proof. So why should it terminate? So let's see a proof of this. So it can be shown that it terminates. So why it terminates? The process terminates, and let's see that. Process terminates. Let's see that. So what do we mean? We mean that at the end of the process, we should be able to have the entire fx written into irreducible factors. So we should have some hj of x which separates any given which distinguishes irreducible factors. So I would write it even more clearly. Let me just do that. Let me just do that. So terminates, I would also write them that what does it mean. So it gives. So I would just mean gives all irreducible factors. Gives all
अब पार पात गया
irreducible factors. So suppose f1 of x and f2 of x are irreducible factors, of fx, knowing the termination of the method is very important, otherwise we cannot write a computer program. So then, so I have two factors f1, f2. Suppose I have two factors f1 and f2, irreducible factors of fx. Then there exists cj1. So I'm just and using CRT. So j2 in fq such that so cj1 modulo fx and hx cj2, sorry, modulo f1x f2x. So 1 less than equal to j less than equal to k. Yeah. So that is what is given by the process. Now what we have to show is that these vectors, so all of them cannot be equal. So all of them cannot be equal. So that is we have to show that. Now suppose that they are all same. So this is equal to Cj for all j. So if this happens, then these factors f1 and f2 cannot be separated using these polynomials, because all of them would assign it to the same element of fqn. Sorry, fqk. So so this polynomial would reduce to the same vector in fqk. So if these all equal. So now since any linear combination so these are all vectors of the null. So they correspond to the basis of the null space of this b minus I. So any solution, any solution. So since any solution, so any solution to this equation that what was our number? I just want to check the number. So yes. So any solution to 4, this equation, so can be written as a linear combination of vectors of the basis vectors of the null space. So let me just come back here. Yeah. So any solution to 4 is a linear combination. Any solution belongs to the null space, so they have to be linear combination of the basis vectors. Linear combination of okay, so I've just basis vectors. Basis vectors. So therefore, and solutions to 4, I just go like this. So solutions to 4 gives solutions to this thing. What we write is solutions to 3. So solutions to 4 are gives rise to solutions to 3. So that is how we construct it. So let's go back. So therefore, any solution let's is hx is a solution hx of three is a linear combination of h1x hkx, because these are actually corresponding to, they are constructed out of basis vectors of the null space. So any solution corresponds to a vector in the null space. So any solution of this system can be written as a linear combination of these solutions. So H1 to Hk. And now we have assumed that for all of these, so all these the solutions, these polynomials corresponding to the basis vector reduces to the same element, that they are equal modulo f1 and f2. Uh, so therefore, this is true for any solution. So then Hx is to some C. So if they are equal, then we get the same linear combination. So this is equal f1x and modulo f2x. So when we reduce, we get the same thing. So this is from here. So just write it 5 or something. So this is from 5. This is from 5. Yeah, but that is certainly so it cannot happen for all solutions just because of CRT. So just because of CRT, uh, because for any alpha 1, alpha 2, alpha k in if qk, for any k tuple, there exists hx satisfying satisfying alpha j mod if jx 1 less than equal to j less than equal to k. So in particular, there exists hx such that hx is say 1 mod f1 of x. That should always be possible, and 0 mod f2 of x. So therefore, this 5 cannot hold for every such solution. So that's a contradiction. So yeah, so we add a page. Or you can just write here, this is a contradiction. So, mm, yeah, this says that this I mean, just for one line I didn't add a slide, so it became a little clumsy. I would write it out more clearly. So the process terminates. The main thing about the last discussion is that the process terminates, and the process is described by this algorithm. So let me just repeat the algorithm, which we would work out examples tomorrow. So we start with a monic polynomial over fp of degree n, and the first step is to consider x to the ip for all these powers. So 1 x to the p, x to the 2p, x to the 3p, up to x to the n minus 1 into p. So we consider this n powers of x, starting with the 0th power. And that so these powers we reduce modulo fx. So once we reduce modulo fx, we have these polynomials. And once we bring out all these coefficients, we gather the coefficient to form a matrix, so which we call B. And we look at B minus the identity matrix. So AI is the n cross n identity matrix. Now the null space of this matrix gives us the solution. So how do we go about that? So if the null space, the dimension of the null space is going to be equal to the number of irreducible factors of fx. So if that dimension is 1, then we just stop. If the dimension is more than 1, then as we have noticed that the first basis vector is going to be this 1 0 0. So we start with that vector. That vector will belong to the null space by our construction and construct a basis. So we construct a basis starting from this. And for each of these basis vector, we construct polynomials, and then we use our first theorem. So we write fx as a product of GCD of fx and these polynomials subtracting this c, which runs over the finite field. And if this doesn't factor, so we start with H2. We have all these k polynomials at our disposal, k minus 1 polynomials. So we start with the first one. And whatever factorization, we may not get a factorization. It might just be trivial. No, so the degrees are all less than equal to n minus 1. So it will give some factorization. And then we go to the whatever factorization we get, we go to the next step till we get all the irreducible factors. That's the algorithm. So we would just do it step by step with examples tomorrow. And I just wanted to point out, I would also talk about that tomorrow. So the thing is, here we are taking these GCDs for every element in FP. So if P is large, then we would be doing many GCDs. And that's a time consuming process. So that takes a lot of time. And that computation is time taking. And the point is that many of these GCDs are going to be 1. We would see in the example also that many of the GCDs will be 1. So there is a modified algorithm which is called Cantor-Jassenhaus algorithm. So that algorithm takes the GCDs. So the thing is that the first step of that is to characterize this C for which GCD is not 1. So once you know which C has non-trivial GCD, you can only look at those. So that will reduce the computation. So we won't be doing that. We would just use this directly for small p. So I'll stop with that. So any question is welcome.
Participants, if you have any questions, you can ask. So, okay, sir. Thank you.
Okay.
I think no questions of an audience. Tomorrow we'll see, sir. The tutorial class.
Yeah, sure.
So, thank you, sir.
For the lecture,
Thank
sir.
you.
Thank you for your nice lecture, sir.
Thank you.
Thank you, sir.
And for tomorrow's tutorial, obviously there is no tutorial sheet. So because I would be working out examples. So
Okay, sir.
Okay, sir.
and I'll forward this write-up for you.
Okay, sir.
Bye.
Thank you,
sir.
sir. Thank you, sir.
Good night.
Good night, sir. Thank you.